Today we are about to learn about why the data path cycle has a huge impact on the performance of the CPU. The data path cycle has a huge impact on the CPU performance because it directly affects how efficiently the CPU processes and executes instructions. The data path refers to the internal components and connections of the CPU that move data between registers, memory, the ALU, also known as the arithmetic logic units, and other parts of the processor during the fetch, decode, execute cycle, which we treated in our last video. Here's why it matters for performance. Instruction throughput. The data path determines how quickly the CPU can fetch, decode, and execute instructions. As a well-designed data path allows the CPU to first fetch multiple instructions in parallel, example through pipelining or superscalar execution. Secondly, quickly access operands and data from registers and memory. Efficiently execute operations in the ALU and other functional units. If the data path is slow or inefficient, each instruction takes more time to process, reducing overall throughput. That is the number of instructions that the CPU can complete in a given time frame. Pipeline stages and latency. Modern CPUs often use pipelining, where different stages of instruction processing, that is fetch, decode, and execute, etc., are handled simultaneously for multiple instructions. The efficiency of the pipeline is highly dependent on how the data path is designed. Longer data path delays can increase the latency of each stage in the pipeline, slowing down instruction throughput. Bottlenecks can occur when different parts of the data path can't handle the data fast enough. Example, waiting for data from memory or the ALU, which stalls the pipeline and causes delays. Thus, optimizing the data path helps keep the pipeline moving smoothly, reducing the overall time it takes to execute programs. Another way is the memory access. Memory access speed is a crucial part of the data path cycle. The CPU must frequently fetch data from memory, that is the RAM, the random access memory, or caches, and this can be a significant bottleneck. Cache hierarchy. The CPUs often use multiple levels of cache, L1, L2, L3, to reduce the time spent accessing memory. A well-designed data path with effective cache management can reduce access latency. Memory bandwidth. The data path must be able to handle high bandwidth when accessing large data sets from memory, especially in memory-intensive applications. If the CPU cannot efficiently move data between memory and processor, performance will be severely impacted. Parallelism and multiple functional units. To maximize performance, CPUs often have multiple functional units, ALU, FPU, load store units, etc., that can execute different instructions in parallel. The data path connects these units and allows the simultaneous operations. If the data path can support multiple instructions executing in parallel, it leads to better instruction level parallelism, ILP, improving performance. However, if the data path has insufficient connections or inefficient scheduling, functional units might sit idle while waiting for data or instructions, reducing parallelism and performance. To summarize this whole lesson, the data path cycle directly impacts the effectiveness of pipelining, reducing small stalls and improving throughput, the efficiency of memory access and data transfer, the ability to execute instructions in parallel and manage data dependencies, the CPU's clock speed and cycle time, improving data path through better design, faster memory access, more efficient parallelism, and smarter handling of hazards is essential to maximizing CPU performance. Thank you guys for your time. Bye.